So you are all fine and enjoyed the IIT Indore stay? No? Yeah, okay. Okay, shall we start? Okay, very good afternoon to you all, and I think we are in the last session of the Gyan course, and this part of the course I felt that I will dedicate to organocatalysis. Okay, and so with the discussions what we started yesterday is on the sustainable chemistry part, that we are in a place where we need to think of lessing down the metal catalysts. We know about Higgs couplings, we know about Suzuki couplings, and the reactions are extremely rigorous with high yielding reactions with high enhancer selectivities. But again, we come to a point where we need to think that we should think of economic protocols and most importantly, the environmental concern. So this is the place. That's why I feel that students coming up with organic synthesis background should think about organocatalysis. I've given a name. See, it's written as enzyme catalysis simplified. So we know that how enzymes have been so active. They create stereocenters very specifically. But the only thing what we feel is, the time. The time required is really, it's too lengthy, and I feel that we should think of reactions where we should find a substitution of this faster or this slower reactions. So I think that this is the place where we start attempting organocatalysis, and to simplify some simple words about organocatalysis is that it's an acceleration of reactions with an organic compound and does not contain a metal atom. So we feel that we should have an organic substrate and also an organic reactant, preferably a catalyst, and that drives the reaction, and we get a fantastic product with very nice enhancer selectivity. So we talked about enhancer selectivities yesterday. Also we saw molecules of multiple chiral centers. So if you look into this, the first one what we discuss about the reaction pathways, and the first thing what comes to my mind or any organic synthesis mind is an iminium catalysis. So you can see that it goes through via a covalent activation complex. You take a carbonyl, you take an amine, form an iminium, and then there is a deprotonation to generate a new organic fragment or new organic ammonium molecules. So this happens to be through non-covalent activation complexes, basically hydrogen bondings or ion pairing, and most importantly, it generates a CC bond forming reaction. So we feel that if there is a carbonyl, there is an activation of proton, and then further it generates a carbon-carbon bond. This is where we achieve an organocatalyzed CC bond generation. Okay. So what are the advantages of organocatalysis over metal catalysts? Many metals are poisonous, we all know, which often present a problem with production process in chemical and pharma industry. So we discussed about, yesterday, making of molecules, the cost related with molecules. Again, you see this, we use a binap, this is what is a chiral ligand in the synthesis. What do you generate? You generate an L-dopa. So what is L-dopa? L-dopa is a drug which is given to hypertensive patients, especially when they, female patients, when they undergo pregnancy. So this is something which decreases the high blood pressure, particularly in pregnant women. So it's very important drug, but you see, how do we synthesis? How do you synthesis? The first step, just see. Do you know what is we use a rhodium cyclooctadiene BF4 as a catalyst in this industrial state. Not only this, we use a 3 bar pressure, 50 degrees centigrade, very high yielding, enhances selectivity definitely. But what is the cost of this? It's too high. If you intend to buy rhodium cyclooctadiene complex to go for 1 kilogram reaction, we need at least 3 lakh rupees for this catalyst. So you can understand that when you generate L-DOPA through this metal catalyzed reaction, the expense for making this old L-DOPA tablets becomes very high. Thus, we feel that there is definitely a need to replace very high expensive transitional metal complexes in such reactions. Not only this, it's also very poisonous and it pollutes the environment. So all these things lead us to a place where we feel that organocatalysis comes to be very, very important. And thus, we feel that what are the replacements? So we know about stannic chloride, we know about BF3. You can ask me a question, sir, why not stannic chloride? Why not Lewis acid like ytterbium triplets? But if you please check this catalysts, they don't give us very high enantioselective conversions. They react very badly with substrates. If you have an alcohol and if you add ytterbium triplet, it's going to dehydrate an alcohol. For example, all such transformations where we use Lewis acids like aluminum chloride, ytterbium triplets, stannic chlorides, all these suffer from many side reactions, what we don't want. Metal-free reactions can typically run under aerobic conditions. Okay, so the best way we talk about publication in journals like Green Chemistry. Why do you do that? Why green chemistry is very important to us? It's important because that gives us a way to support the environment. Often chemists are targeted, especially organic chemists are targeted that we don't follow environmentally, saving protocols. But it's not that. So we feel that organocatalysis, which are substituents to metal-free reactions, we can run in aerobic conditions. I'll tell you a story. When I was doing my postdoc in Stanford, every weekend we are a bit in trauma. What is that? Why I was in trauma as a researcher? Every weekend the cop will come. What is a cop? Police. And the American police is much healthier than us. Okay, they look like police. Okay, and they come with a white handkerchief like this. Very clear. They come to me or every researcher, and we had a sink where we used to work. We had a fume hood, we had our reaction table, and we had also a sink, and the sink had a pipe like this. So it comes straight, there is a curve, and then it falls down. What the cop is to do, it's come and he will tell you that, okay, I'm going to check your basin. They will take this white cloth and just wrap where it is you. And if you find some metals which is stuck there, you are going to be fined. Okay, they're straight away going to fine you with $500 because actually you did not follow the protocol, because you had things where you can dub your metal rests, where you can dub your solvents. You have not done that. So we're very cautious. Definitely, the foreign or abroad people were much conscious earlier. That is why they already have been maintaining so many sustainable strategies in chemical synthesis from the very beginning. Now, when we start organocatalysis, the first thing what comes to our mind is a phase transfer catalysis. So what is a phase transfer catalysis? Phase transfer catalysis is a catalysis which is done in between the two phases, right? What is that? What we know in chemistry is one aqueous phase and other is an organic phase. So if you think of phase transfer catalysis, I personally feel that cinchona alkaloid derived catalyst comes first. Then there is a guy called LIGO which has sufficient contributions on such catalysts, and then comes Morocco from Japan, and I will show you one by one, and we will see that slowly we have been developing these organocatalysts under the phase transfer catalysis, and these 2%, LIGO and Morocco, have been very, very strong contributor on that. You can ask me, then why did the Nobel Prize go to Macmillan and Benjamin List? That's definitely true. That Nobel Prize in organocatalysis have gone to these big stalwarts, but again, I'm telling the progress. So it started with LIGO and Morocco. I will also show you that what contributions have come from the LIST laboratory. Okay, but I personally feel that LIGO's contribution and Morocco's contribution has been immensely active in case of organocatalysis, particularly phase transfer catalysis. And the second part of organocatalysis deals with something like proline catalysis and imidazolidinones. Okay, now let us come to one by one. So the picture shows something like what you mean by a phase transfer catalysis. Was this, you can find an imine and an ester and a quaternary salt here. Okay, so this is what is in the organic layer and this is what is an aqueous layer. So when you do something here in between the interfacial, or you find the aqueous reagents entering this layer and the organic layer coming as well and doing this catalysis, it's called a phase transfer catalysis. And see, the reaction happens here in between these two, and that is actually the reason of giving very highly enantioselective reactions. Coming to the next part, what we call is cinchona alkaloids. So you can see that it's nothing but comes from natural products. Okay, cinchonine is about $22.9, 25 grams, and cinchonidine 22.70. But actually they are fantastic natural products having chiral centers here. Okay, fantastic backbones achieved from natural products, and you can use it not only catalyzing your reactions but also inducing enantioselectivity. See, fantastic starting in 2004 by O'Donnell. So this is, I think, the first report what has come to us about cinchona alkaloid catalysis. People did not name that time as organocatalysis. They just told that this is cinchona catalysis. If you go through his review in accounts of chemical research, he mentions that cinchona catalysis. So this is where I discussed with you how synthesis progressed throughout the years. So this is where we should understand, we should know the timelines, how the chemistry has evolved out. So it's 2004, and it was not List nor Macmillan. It was this guy, okay, who started the concept of actually organocatalysis. He termed it as, cinchona catalysis. Now, let me come to this. He immediately prepared 3 catalysts. The first one he termed as generation 1. We call generations like we feel, no? That our grandparents, then our parents, then us. So these are what generations, what we mean when we talk about our society, our families. But in catalysis 2, we term them as generation 1 catalyst, generation 2 catalyst, generation 3 catalyst. We know about ring closing metathesis. What is the catalyst? Grubbs catalyst, Robert Grubbs, who won the Nobel Prize. But was that the first catalyst which was discovered? No. Before them, there were series of catalysts. Even after Robert Grubbs, Richard Schrox developed molybdenum-based catalysts, and they also used it for ring closing metathesis. So what we develop is, there's a continuous development of catalytic chemistry. Generation 1, generation 2, generation 3. The same thing happens in transition metals as well, but I feel that in phase transfer catalyst, the first one is this one, which we called as generation 1. And the second one, what they tried, particularly the LIGO's group, they substituted this OH with an allyl bromide. So this is a simple reaction. If you treat this with sodium hydride and allyl bromide, you get this O-allyl. And this is what is the second generation catalyst. The only difference was the allyl bond. Okay, nothing else. Now this slowly came, they thought that why not make it more bulkier so that the enantioselectivity generates very high. In that case, they replaced this benzyl with what? What is this? What is this backbone? What is this backbone called? Anthracene. So, see, I always tell my students to visualize molecules. Can you visualize this molecule? So you cannot visualize molecules methane like CH4. The moment I say CH4, what should a synthetic chemistry student feel? It's that pyramidal geometry, right? You should not write CH4. The moment we say methane or ethane, what should come to your mind? You know, the staggered formula, right? Similarly, can you visualize this molecule? So complicated, so big. Like this part is actually covering, so there is a small cavity inside where the reaction should happen. This way. So we have to visualize the organocatalysts. These are the cavities, we generate the cavities so that the enantioselective transformations happen inside. Okay? So I think that these three, first one is the generation 1, second is an allylated molecule which we call as generation 2, and the third one, they replace the benzyl with an anthracene and we call it as the generation 3 catalyst. These are all based on the Syncona based for phase transfer catalysis. Now let us see the first use by Donald. See, fantastic, JAKs 1989. You see the enhancer selectivity. What they do, they go for a substitution. They take an imine carboxylate, use generation 1 catalyst, simple base like sodium hydroxide, dichloromethane, room temperature 15 hours reaction. No high temperature involved, no exhaustive condition involved. Reaction in a phase transfer system where you have DCM and sodium hydroxide in water. And you use this catalyst, the generation 1 catalyst, and you get a yield about 95%, but 64% enantioselective excess. When you crystallize it, when you crystallize the molecule and deprotect the ester, you get an yield of overall 50% and very high enantioselectivity, 99%. See, we generate this molecule, but there is no metals involved. Did you find any metals here? No metals. No metals, room temperature reaction, organocatalyst. Organocatalyst means very small use of this catalyst. I have not given you the catalyst amount. I did not mention the mole percentage because they have also not mentioned, but what I feel is it's very less amount they have used. But see the overall reaction, 99% enhancer selectivity. Even we struggle. Even in today's day, when we try to develop asymmetric reaction in our laboratory, it's very tough. We struggle to get 80% enhancer selectivity with all modern instruments. But you see, 1989 in JAKs with the first generation catalyst, he gets an enhancer selectivity of 99%. Very, very fantastic results I feel in that time. Now when he does the same reaction in generation 2 catalyst, see, just remember, we use an allylated one in this case. So he tries this reaction with generation 2 catalyst, 95% yield, 81% enhancer selectivity. There is a catalyst, and you can see that what I have mentioned is an experiment 1, 2, 3, 4, 5. When they take the catalyst like tetrabutyl ammonium bromide and there is no benzyl bromide, the product is 100%. The racemization percent is 0. Generation 1, generation 2, generation 3. What they want to say is that the racemization study to detect what is the active catalyst species, and they end up with nothing. See why this table is given. So we do the reaction. We do the reaction here. But how does the enhancer selectivity come? How does the enhancer selectivity arrive here? 81% enhancer selective. How does the reaction go? So what I mean to say is that when we started this chemistry, when we started the organocatalytic chemistry across the globe, what appeared to us was it's not a simple carbocation, it's not a simple carbanion, it's not a normal simple iminium ion intermediates. The reactions, we knew only a few things. The reactions were happening in catalytic mode, there were no metals, reactions were happening in water, inside the phase, but how does the reaction happen? How does the natural selectivity come up? We were not sure about it. What is the mechanism? Because we need reactions, we need understanding of mechanisms. That what is, so in an SN1 reaction, what do you generate? You generate an SN1 reaction. The intermediate is a carbocation. How do you understand? You understand with a reverse observation. What is the observation? You end up with a racemic mixture. Okay, in SN2 reaction, you don't get a racemic mixture. And we think about, okay, this is the first one is an unimolecular reaction, the second one is a bimolecular reaction. But what type of molecularity or what type of mechanism was actually operative in organocatalysis? We didn't know. We did not know what is the intermediate. We only knew that, okay, we are using generation 1 catalyst, we are getting this yield, we are using generation 2 catalyst, we are getting this yield, this is the enantiomer selectivity. Now, the third generation, please see, Corey comes up. So I told about you in Corey, he's one of the big shots, Nobel Prize winner, fantastic contributions in organic synthesis. So far, Corey was not into organocatalysis, but when he found that, okay, some other groups like LICO are very prominent in organocatalysis, he comes in with his first publication in 1997 in JACS, and this is the report what he shows, that the first one, same transformation, you see the transformation, you have the imine, you have an alkyl bromide, and you have the catalyst. In one case the catalyst A, what they use 10 mole percent, and the other case is the catalyst B, they use the same 10 mole percent, 50% of potassium hydroxide, toluene, cesium hydroxide, and DCM. Room temperature is 18 hours. Coase condition shows minus 78 degrees centigrade, 23 hours. LIGO says 94% enantiomer selectivity. Coase says 94% enantiomer selectivity. 68% is the yield, 87% the yield. Now you tell me which is better. LIGO, a young person that time. Coe, a very big shot in Howard University. And they propose a simple reaction. Catalyst A by LIGO, catalyst B by Coe. But what is the difference between catalyst A and catalyst B? What is the difference between catalyst A and catalyst B? Is there any difference in the counter cation? What is the difference? In the first case, you have, can you find the difference? Very interesting chemistry. Why did I pick up? Very interesting chemistry. Try to understand. The backbone is same, but you change the anion. In first case, the anion is, the second case, see, you try to feel the chemistry. In one side, when organocatalysis started, we don't know what intermediates they are following, because we read what? We read traditional intermediates, carbocation, carbanion, okay, nitrines, carbenes, and suddenly we come up with a reaction where we find that there is a catalysis, and that's done by another organic compound, and they are showing fantastic observations like the one which is reported by LIGO in one side has a chloride anion, and the other one reported by a very big shot like Professor Corey, and it changes just bromine, and there is a competition between these groups, and both of them report in 1997, right? One, LIGO, young guy, so it could not publish in a very big journal. Okay, it goes in Tetrahedral letters, and Corey, his name is sufficient, goes into JACS. Okay, but my question to you is, what is the better reaction? LIGO. LIGO is the better reaction, but it went to, okay, and what do you think is not a good reaction goes into JACS. Okay, so it's not 2025, it was also there in 1997, and it will also be there in 2050. So you should accept it very sportingly. Okay. Now, but the other important thing is that when we find that a 50% KOH and room temperature reaction does fantastic enantiomer selectivity, only the yield is little bit less. Whereas why do you use lot of energy, minus 78, 23 hours, to give us 94, the same enantiomer selectivity, a little better yield. But that's okay, that's fine. But organocatalysis is something we should look into in a different eyesight, because here not only the cation but also the anion was playing an activity. We normally leave it, whatever you have. We don't think about bromides. We don't think about anions like fluorides in the system, and we concentrate only on the cationic part. So this is a message to all of you. who have been working now in research labs, in industrial labs, and also in future, don't leave a reaction just sir ये नहीं गया है. If this type of change in organocatalysis or this type of beautiful reactivity can be seen by just changing an anion which is quite far from your reactive center, then you should try all sorts of variations in any methodologies or any role synthesis you're working on. So this is my message to all the students, that a small change, what we cannot expect, is also does it. Okay, you did not follow one more change in the catalyst. One had a double bond and the other did not have a double bond. But again, it's a straight one. It's a straight 2-carbon system. So it's very tough to explain that what actually catalyzes, but later on it was cleared, but it's definitely the anion catalysis. Okay. Now, to understand the systems, there was a lot of deliberations that how these reactions are catalyzed, what is chlorine and what bromine, and there's some explanations which are also clear in these 2 papers, but there is a long explanation. It's nothing but due to the cavity where inside which the reaction happens, and they say that we are really sorry to make you that we are unable to understand that how chloride and Br minus is actually giving so much of difference in the system. So this remains unexplained even if both this group has written 1 or 2 reviews on this article. Okay, but one thing was understanding the ion pair. So there was something which was playing the cation and the bromide interaction, or the cation and the chloride interaction. So there was something what was playing the ion pair interactions is very easy. It was something which was I'll say that very important for understanding this enantiomer selectivity. So please take home a message from this reaction that it's not only the main reactive center which plays an important reaction, important decisive systems in your reaction, but also the anions which are playing very important. So if you set a series of reactions to understand your systematic methodology, I'll suggest you, even in photocatalysis, you should try with systems which have different anions. Okay, it's not only the cations. Okay. LIGO has been, as I told you, that we all know about Macmillan and Benjamin List, but I think LIGO's contribution was immensely powerful. You can see that he has prepared a huge library of his organocatalysts, and he does it, or he starts from this, this type of tribromo biphenyl type molecules and go for a boron and palladium couplings to finally give up this type of 7-membered ammonium counterparts, and the term is catalyst. I've given as catalyst A, but you can understand that they can have a series of this. They can change the substitutions, the R's, and they make a lot of libraries. Okay. So, now the next part. So, see the transformation. Okay. 10 mole percent. This 10 mole percent. Just see this. Catalyst A as 1 mole percent. So see the change. 1997, 2023 and 2022. So we come up a place where we have started developing in the organocatalysis fragment. How do you develop? How do we say that we are developing? We say when developing when we find that we are using very minimal amount of catalyst. So there should be a mark. Often students, and when we deliberate lectures or we compete, we give competing lectures with other faculties, we try to establish ourselves. How? We say that our systems, our synthetic methodologies, our total synthesis is better. But what is the quantification? When can I say that I have done the same natural product is done by Professor X and Professor Y, and I say that I am the best? How do I prove that? I prove that saying that when I use the minimum amount of catalyst and my overall yield is very high and the enantiomer selectivity is also very high. But the main decisive factor is what amount of catalyst you are using. So you see that now they have come to a place where the organocatalysts, so organocatalysts, as I told you when we started, enzymes, less timing, more amount of enzymes. See, I have a whole series I can deliver lecture on enzyme catalysis. What type of enzyme catalyst we use? We can use wholesale catalysts. We can isolate enzymes. But you see how much of enzymes we require for a transformation of 1 gram material. You can visit industries like AstraZeneca, Novartis. You can see that they have series of labs in enzyme catalysis. But how much of enzymes they use? Huge amounts. Ultimately, in the whole 2 days or 48 hours reaction, you will find that 1 gram of material has been converted with very good enhancer selectivity. No doubt with enhancer selectivity in enzyme catalysis. But time, 48 hours, 72 hours, yield 20%, 30%. So, how do we develop? We develop when we say that we have developed in a sense that we have come to a place where we are using a catalyst with 1 mole%, 30 degrees centigrade, room temperature, close to room temperature in some cases, and delivers complete conversion of the product. And this was done already in 2020, 2002 by this group, by LIGO, okay? Not only this, he tried to manufacture different fragments. He incorporated CF3s, trifluoros, tertiary butyls, methoxides, try to increase bulkiness, molecular complexity. So he wanted to increase complexity in his catalyst. And you see 97% enhancer selectivity, 92, 86, 55, 89, 95, it's fantastic yields. But again, it's not the carbocation chemistry. It's not the carbon ion chemistry. If you ask me, so why did it go? When I take ethyl, you can ask me, so when I change the alkyl group to ethyl, you see that enhancer selectivity reduced to 55%. Why did it happen? And frankly speaking, at this moment, I am not in a position to answer this, and neither the authors, because they have tried to explain using ion pair interactions, because we cannot tell any other mechanisms involved in such organocatalytic reactions. There's something what we achieve after we do the reaction. We try to explain, but exactly it's very tough to explain that why we change R with tertiary butyl, very high yield in 89%, enhancer selectivity is 97%, the yield has not decreased so much, but why did we get 55% enhancer selectivity? That remains a question. Again, if you just change the alkyl halides, for example, benzyl bromide, naphthyl, 2-naphthyl bromides and many others, times enhancer selectivity yields, you see that it comes 71%, whereas in this case it's 100%. So tabulation of reactions in organocatalysis like this, we don't have a pattern. You cannot expect a very dedicated pattern as we talk about steric hindrances in our classical chemistry. We cannot explain in that way in organocatalytic approaches, particularly when we talk about this type of very old catalysts. Okay, we know. So what is a Michael reaction? We talked about Michael additions yesterday. So this is a very nice fragment, I would say. What is this? It's an alpha beta unsaturated ketone. Why this is important in chemistry? Because I told you yesterday that it's a fragment where we can do 1-2 additions, we can do 1-4 additions, and you have the independence to add 4 carbons altogether. See what we do. When I started my lecture, I told you that we are very powerful people. Why? We can make molecules, we can give birth to molecules. And how do we give birth to molecules? We need fragments, we can add them. We know the art how to add them. We know the art how to make rings. We know the art how to open the rings or how to close the rings. Okay, so we know it. But again, we also need, as I told you about toolbox, we also need fragments. One fragment is this, alpha beta unsaturated. The other fragment is cyclopropanes. We can open it very easily, add it anywhere. So this type of fragments, I feel, is very nice, and we should give a special consideration in creation of chiral centers in asymmetric Michael reactions. The same was done by this group, by LIGO, and he says that if he adds 1 mole% of his catalysts. So how do you do a normal Michael reaction, MSc students? How do you do? You need a base, right? Why you need a base? We need to generate a carbon ion, and that adds to 1,4 or 1,2. If it's Michael, it's 1,4. But what type of base we need in Michael reactions? Do you remember? If you want to generate a carbon ion, for example, alpha 2 and carboxylate ester, what base you use? Very non-nucleophilic, it's fine, but very strong base, isn't it? Like potassium tertiary butoxide. So, potassium tertiary butoxides, and what is the condition? You cannot open potassium tertiary butoxide like this and open it. You can do it, but there are a lot of problems, like it absorbs water very fast. So what is the best way you do? To generate freshly prepared potassium tertiary butoxide, you have to cut potassium. How to cut potassium? Can you cut the potassium like this? Like you cut a cake? ऐसे काटते हो? कैसे काटना है? Very tough. How do you do? We hold it like this, put it inside a hexane or plate ether with one hand, and you catch another hand or knife, put it, and then the moment the solvent goes, what happens? And I have the very worst experience, I was admitted in 17 days in hospital during my PhD. I had a skin grafting, skin from here to there, because there was an explosion. And there was also a potassium tertiary butoxide. So it's not easy. So please, why I am telling you this story? Because it's not easy to do this classical reactions. For example, this Michael additions with potassium tertiary butoxide. I am talking about, my accident was in 2008. And that time we did not have freshly available potassium tertiary butoxide, what we have available now from Sigma Aldrich. So I remember that it was a festival day, and I came to my lab with my slippers because I thought that I will just put the reaction and go back to my hostel. And I went to the hospital. So okay, so it was severe problem, but that is okay. That's a part of hardships we take in research. That's okay. But the thing is, what I want to make you realize is that the classical chemistry was not so easy. We needed, for a simple reaction like this, we need to have such reagents, and the availability of reagents were not so easy, unsafe, very, very dangerous to use. But we were compelled to use. See, I was doing a 1 gram reaction. But just understand, if I need to do a 100 gram reaction with potassium tertiary butoxide, in those days, how much of potassium I need to cut and set this reaction. It's very, very unsafe. But you see, when organocatalyst came up, it became so easy. And they did this asymmetric Michael addition, cesium count, very stable base, no need of potassium tertiary butoxide, just 1% of Ligos catalyst does an asymmetric Michael reaction with very high enhancer selectivity, in some cases with a pure one, definitely some time, but that was developed later on. But you see, 94% of yield with 94% of enhancer selectivity, particularly the enhancer selectivity was really nice. But again, I tell you, tertiary butoxide, tertiary butyl as substituent, you may ask me, sir, why it is 60%? I do agree. I told you that it's all about the ionic interactions, the cavities where the reactions happen. And it's very tough to exactly explain the changes in the substitutions and this enhancer selectivity. So 45%, certainly it goes down, and it goes up here with benzyl, it goes down with tertiary butyl, enhancer selectivity goes down. So how do you explain? But that's not the important. The chemistry is that what we use and what we used to use. That is important. So we rise fantastically on the field of stereoselectivity and also ease of reaction when we think of organocatalysis in this case. Okay, this was a time in 2005 when one of the most lovable persons, I met Muroko in numerous occasions, fantastic thin and lean person with long hairs. Okay, Muroko is from Japan. Kiji Muruoka, full name. He started his chemistry as an independent researcher with his numerous backbones, ammonium backbones. But this one, I tell you that even anyone in the world is now working on this catalyst, or not catalyst, but the backbone. The backbone he made. This is the backbone what he has made of an ammonium salt. Fantastic work. This backbone is one of the best backbones where we can induce enhancer selectivities in any reaction. The moment you read his work, okay, it's something like this, an eye-opening for you. Why do I say it? Because we all work, or we will work in organic synthesis laboratories or any synthetic laboratories, and in any case, if a situation comes to you, your group leader or your boss comes and says you that you need to do this asymmetric transformation, and I want a fantastic enhancer selectivity. The first thing which comes to our mind as a student is, सर ने तो ये बोल दिया, लेकिन मैं शुरू कहाँ से करूँ? I mean to say, which ligand I'm going to use? Are we going to use BINAP? Are we going to use synchronine? Are we going to use anything else? But I tell you that this is a fantastic backbone. It's majorly very, very successful, as a whole, as inducing enhancer selectivity into any systems, any reactions. We have seen that. So it was the first report in 2025 in Pure Applied Chemistry by K.G. Morocco, where he showed these wide sections. He's just synthesized these molecules with very nice enhancer selectivities. He showed how we can make this backbone. We did not know what he has made, but he explained the structures. He told that this is the first time where we synthesize some ammonium phase transfer spiro type of catalysts, and they gave this nomenclature and published in JACS in 2023, but they did not show the application. They just synthesized them and put it through. Later on, this has become, I think, one of the most stalwarts catalysts for inducing enhancer selectivity. Pure Applied Chemistry in 2005, one of the first reports where they were working on the protein chemistry, and they show that they use first time this backbone ammonium bromide, or I would say today's day we call it Morocco catalyst, and in alkylating this position of imines. See, we had also used in earlier cases, we showed this reaction, but you see the substrate cope. He has added allyl bromides, propargyl bromides, benzyl bromides, many bromides are alkylating this position. Potassium hydroxide, fantastic reaction with water. But one thing I did not understand in the reaction, why did they use argon? Why did they use argon? Because normally when we say that it's 50% of aqueous condition, okay, it's already water in it. And when there is water, there's no need normally to add argon. But they have used argon as an inert atmosphere. So this is a part which remains unclear to me after all these 20 years, that why exactly Morocco, because this is stable, this part is entirely stable in water. So actually they did not need to use argon, but I possibly feel often what happens, our students are overcautious. Even they don't need nitrogen, they add nitrogen in the reaction so that kuch kharab nahi hoga. So it's something like this. So they should have understood that they're using, or the student should have understood that using aqueous potassium hydroxide. So when you are using water in it, so there's no need to make it an inert atmosphere. But however, the enhancer selectivities in all cases, just see 99, 99, 99, 96, 99, 9, very, very high enhancer selectivity. So I think this was one of the first applications where we use an organocatalyst to go for an alkylation of a glycine, and it gives us 98 to 99% enhancer selectivity. Catalyst used is 1 mole %. Not only this, they have also used it for synthesis of pharmaceutically important natural products like ACE inhibitors. You can see they have done multiple step reactions, finally delivering this inhibitor with fantastic yields and enhancer selectivity. Okay, fine. Morocco goes on high, and now he comes up in 2005 in a report in Agrivende where they say that we make it unsymmetrical. Initially it was a symmetrical spirocatalyst. So if you just compare with this catalyst, see, We have similar backbones in one side, only there was a change in the fluorides. Now they say we come up with a more efficient catalyst and we have long chains like this. They describe it as more efficient catalyst. Why? Fantastic structure. You can see that they are well established structures, crystal structures, but they say that we get 98% and 99% enhancer selectivity published in Agrivende in 2005. But how it is superior? How this catalyst is superior? Same reaction, same alkylations, they call it superior. Kyun? Where? So we come back to the original thing what I say. When we say that we are developing, we say that we are developing when we say that see the catalyst amount they have used. How much catalyst amount they have used? 0.05 mole percent. You remember when we started, it was 10 mole percent Syncona catalyst. Okay? 1978. 2020, 2005, Morocco comes up in Japan with a system like 0.05 mole percent published in Agrivende. So just see the development. Okay? Just see the development through 25 years. We come up with a very fantastic catalyst in this type of alkylation with very high yield and very low, catalytic amounts. Okay? But again, this is what they mention under argon. But they use 50% of aqueous potassium hydroxide. So that is somewhere we need to think. Okay. Lot of other reactions, what they mention, throughout the chemistry. So Morocco had one of the biggest groups in Japan also till now. I think in any time, not less than 60 students work with him. Okay, very, very big group in Japan. So, a lot of chemistry. In all cases, they use 1 mole percent of catalyst delivering all these shots of alkylation. And this is an example where they show dialkylations as well. Why this is important? So let me ask you a question. Just forget it. If there is 2 hydrogens, do you have a reaction where you can do dialkylation in one step? Not step by step. Normally what do? We use sodium hydride, okay, or potassium tertiary butoxide. But have you tried this reaction any time? I'll take an alpha beta unsaturated ketone. There is a CH2 and this methylene. I'll alkylate all the 2 hydrogens in one shot. Very tough to do. Not possible. It's not done. You need to alkylate it first, one step. Then you need to do workup. You need to purify in column. You need to characterize it and then go for the second step. But in this case, Morocco says that, or he proves that his catalyst, which is catalytic with very high enhancer selectivity, goes for dialkylation fantastically without stopping the reaction. Okay? So now if I ask you, or if I give you a question in any of your examination that give me a condition where I need to alkylate a CH2, which is alpha to any ester or whatever it is in one step, dialkylation. So you should mention the Morocco conditions. Okay? Very good. Now, conjugate additions to alpha beta unsaturated ketones. Okay. Have you done any reaction in nitromethane? So when we add nitromethane to any aldehyde, what is this reaction called? Sorry? Nitroaldol reactions. Okay, nitroaldol reactions are very good reactions to incorporate nitrogen into the systems because they're efficient, very fast, very reactive, and can be manipulated to many other nitrogen systems like amines and amides. In the same direction, Morocco try to find out if they can add this nitro backbones into the alpha beta unsaturated systems with their catalyst. And they found that yes, it's definitely occurring, but a mixture was available like 96%, the syn isomer, and also the 4% with anti. It happens to be in minus 20 degrees centigrade. So this is another functionalization what Morocco uses. Now, What is the name of this fragment? There is 2 nitrogens and 1 carbonyl. Any idea? You have something called, the nitrogen system. So what will be this fragment called? Fragment. This fragment, urea is a molecule. Okay. What is this fragment called? Carbonyl, N in one side and the other N in other side. Urea is a molecule. What is in urea? NH2, CONH2. So I want to understand that if you remove one hydrogen from one nitrogens both sides, what is this called? What is lactam? What do you mean by lactam? There is a ring, there is a CO and there is NH in one side. It's a cyclic amide, right? So now in the cyclic amide, carbonyl, nitrogen, carbonyl, carbon. Now this carbon I am replacing with another nitrogen. What I will call? Okay. So important question for examination. Okay, try to find out. So why this is important? Because we have found that in all rings, if a system like this happens, or if you get a moiety like this, carbonyl, nitrogen, that's very common, lactams, another nitrogen, it shows fantastic cell adhesion inhibitor activities. This is a very prominent cell adhesion molecules, and Morocco came up with this biaryl catalyst. They just increased this side. So they made this biaryl backbones. See the fragment changes. This was one fragment. This was another fragment. This is another fragment. So they're changing, they're playing with the catalyst. This is what you're doing. You're playing with the catalyst. And they're showing one by one. And all in good journals. This came in tetrahedron, not so high, but it's okay. He published Angle One Day, Pure Applied Chemistry, many things. He's just playing, what I feel. So you should enjoy the chemistry when you read. He's playing with the catalyst, changing the fragments, and using it in creation of very high yields and by enhancer selectivities when they do this reaction. Okay? Now, we come to the next part from PTC to enamine catalyst. What is an in and amine? What is an in and all? What do you mean in all? What is an in all? In all. In amine. So in all you have a alkene and all or alcohol, right? And in amine you're having an in and amine. Okay. So both this enols, you all know that how enol is important because we all know about aldol reactions, enhancer selective aldol reactions. The best way to generate a CC bond without involving any metal catalysts. Okay, and that's true enhancer selectively. In similar pattern, when we come to in amine catalysis, I think this is also done tremendously beautiful reactions. So if you see that how an enamine generates or catalyzes, so you start from a carbonyl and you generate an imine. You can react with any amine like this and generate an imine. You lose a proton, comes to an amine again. There is another fragment which is a double bond. There's an addition to this carbon, and then you generate this fragment and the amine is freed again to go for another cycle. So this is what is a very simple explanation how an enamine catalysis can happen. It can come from your organocatalyst. Okay, fantastic simple proposition. So once I was attending to one conference in SIOC, Shanghai Institute of Organic Chemistry, and there I think Professor Macmillan was giving the end lecture, and Dean Toste, Professor Toste from Caltech was giving the inaugural lecture. And Professor Toste started the conference in SIOC saying a word called perception. He told that I feel whatever I have done, it's just because of perception. On a lighter note, when Macmillan ended the conference, so one was giving the inaugural address and one was giving the ending address, fourth day. Then Professor Macmillan was also there in the first day and he was listening what Professor Toste was giving. And Professor Toste said that I worked with organocatalysis, I worked in gold catalysis, and I feel that everything you do is perception. Macmillan the last day said, not pointing him but to the audience, that someone said that the perception is the only thing that has made us work, but I feel it's not perception, it's only what? It's only dedication to work and nothing else. So the first, see, there is competition, as I told you yesterday. There was competitions to tell that who has given the first arrows in chemistry. There was competition to first who will announce the correct steroid nucleus 50 years ago in MIT. There are competitions still now. So one person thinks, one stalwart thinks in chemistry that it's only perception, thinking that the mechanism should work like this. Whereas the other person thinks, no, it's not perception. Is that how dedicatedly you are working in your fume hood. That gives you the results. Anyway, we feel both are correct. So this was the perception when enamine catalysis started. Okay, so the first one came up with some unknown groups, I think, Richard and Parrish. They say that they claim to have the first proline catalysis in very beginning, 1971, and they show that they use this proline 3% for an aldol type of cyclization. So it's a proline catalyzed, they generate the cyclic diketone from this type of 6-exocyclization, where they say that it's S-fluorine they're using as an organocatalyst, fantastic 6-exo with 93% enhancer selectivity, and also they use similar conditions where they show 71% enhancer selectivity. Yeah, okay, fantastic. So this was a starting where they say that this is nothing but an enamine catalysis and it's catalyzed by fluorine 3 mole percent. Not only this, now big shots try, something comes up, what I feel, and then some big shots start putting up efforts. So this is the first thing. List got Nobel Prize in organocatalysis. So his first reports were this. In 2022 and 2024, he reported the same enamine fluorine catalysis to generate this type of aldol type reactions. Yields were moderate, 60 to 90%. He generates this, he adds these aldehydes into this carbonyls using S-fluorine. 10 to 30 mole percent they used. Very high mole percent of fluorine catalysts. List group, very big group in Max Planck, right? Very big group. So they started with the good catalysis, but the only thing was 10 to 30 mole percent. But I already told you that we say that we want to measure the catalyst amount when we talk about this type of catalysis. Okay, so 5 to 35% fluorine catalysts in the next case. Okay, although the enhancer selectivities were good, 90%, 99%, but again, the results indicated 5 to 35 mole percent of B used. See, now you tell me, who was best, LIGO or LIST? You remember the person LIGO started organocatalysis in tetrahedron papers with 10% catalyst, and LIST starts a fluorine catalysis. So LIST was not the first. I wanted to highlight. LIST started fluorine catalysis, but LIGO started organocatalysis in 1978. LIST came much later in 2002, where he showed fluorine catalysis, but again with a very high amount of catalysis. Okay. Now, directly coming in, I don't explain because I personally feel that there are much other contributors, and I will show you that how others have contributed a lot in organocatalysis. Fantastic report in Science by 2002 by none other than Jacobson group. Okay, very nice report. Why this was important? Because this is the first time when someone said openly that the organocatalyzed reactions are mimicking natural enzymes. Okay, so I started with what? Simplified enzyme catalysis, right? But all this, we started with 1978, catalysts going on, organocatalysts being worked, LIGO, Morocco, list coming in, but no one said that this is mimicking enzymes. So the first report comes by Eric Jacobson in 2002 when he reports in this Science paper that they say that this type of protein or enamine catalysis in the aldol reactions or aldol additions, we feel that it's mimicking natural enzymes like class 1 aldolases, and immediately the paper gets accepted with proper explanations in Science in 2002. You can see that they propose that this is a substrate, they undergo the reaction similar way we showed, right? This is the common one, how it reacts. So he says in similar way that the substrate goes for an enamine generation, and this is the proposed transition state. We add an electrophile from here, finally delivering the product and releasing the protein for taking another cycle. And this is exactly what is mimicked in enzymes. And this was reported by none other than Eric Jacobson in 2002, where he says that now we are in a position to say that it's mimicking the normal natural enzymes. So organocatalysts can be thought about enzyme catalysis. Okay, this is one of the milestones I feel that should be reported when we talk about organocatalysts. But surprisingly, when we talk about organocatalysts, we don't speak about this guy. We only speak about Macmillan and Benjamin List. Okay, good. There is another person whose name is Carlos F. Barberis. He is in Scripps. There are two Scripps Research Institute. One is in US, which is close to Stanford, where I told you. And the second one is in Florida. There are two Scripps. Carlos is in Scripps. It's not in Florida. And he comes up in 2006, his group, but unfortunately, I'm sorry that Carlos died 2 years before. He was a very young guy, but he lost his life due to some problems in health issues, but immense contributions, I'll say. Fantastic type of anti-manic reactions. He uses protein catalysts delivering very high enhancer selectivities, 99, 99, 99, 97, L17, 85, 71%. Catalyst loading, which was being used like 30 mole % by Benjamin List. Here, Carlos group shows we use 1 to 5 mole % for delivering such good products, show some complicated mechanisms to deliver this type of anti-manic reactions. Another guy comes in whose name was Takemoto from Japan. So urea, someone was speaking of urea. So he started thinking on organocatalysts where he can develop, something out of derivatized urea. What do you mean by derivatized urea? It's nothing but thiourea. What is urea? CO, NH2, NH2. Now you replace the oxygen with sulfur. What do you get? You get thiourea, right? And what he has done, he has just changed. So this is what is the thiourea backbone, NH2, CS, NH2. Now what he has done is replaced one hydrogen with one big group in one side, and another side he has actually added a chiral group so that they can start enantiomer inductions based on the thiourea catalyst. And you see what Takemoto group reports in this type of enantiomer selective Michael reaction. They use actually catalytic amounts very less, this type of catalysts for, in this case, all the three delivering fantastic enantiomer selectivities. I'll say but yields 86%, 58, 40, in this case 87, 74, 95, 88. So please understand that in 2023, there is two important goals, one by Jacobson, who comes up with this explanation of enzymes, but actually a protein catalysis. In the same year, it's by Takamoto, where he comes up with thiourea-based organocatalyst delivering enantioselective microreactions. Not only this, the next one is something like a pericyclic reaction. Yesterday I asked one question in your class, how do you do pericyclic reaction? And some of you told me, sir, heat or light. Now, this answer in the board gives you a question, gives you another answer. I will not say, sorry, question answer, that is not only heat, not only light, but also an organocatalyst, right? So you see that this was the first report by Schreiner where he uses, see these catalysts were developed actually by Takamoto, but Schreiner uses this catalyst the moment this is out. This type of catalyst are published, Schreiner picks it up and uses it in this type of Diels-Alder reaction. What is a Diels-Alder reaction? It's a 4 plus 2 cycloaddition. We never thought. So why I have kept this in the slide? Because this is an only example where we can prove or we can say that it's not only heat and light which does if a Diels-Alder reaction, but also an organocatalyst which can do a Diels-Alder reaction. Okay, see, he takes an alpha beta unsaturated ketone and a cyclopentadiene, and in cyclohexane he uses this organo or thiourea catalysis to give this Diels-Alder reaction. So the rate is 8.8-fold rate acceleration observed, 8.8-fold rate. Not only this, the computational studies were performed on both the catalyzed and uncatalyzed reaction, and they found that they were much effective in water. Much effective in water. See, this is also very important. You are doing a reaction only having organic molecules. All these are organic molecules, and you can ask my students that did they try to dissolve these molecules in water? They will not dissolve. They will not dissolve. Because why? They will not dissolve because they are organic molecules. But in this reaction, you use water as a solvent. You use the water as a solvent, you replace the cyclohexane. They have done these studies and they found that these cycloadditions can be catalyzed with this thiourea catalysis to give this Diels-Alder reaction, and that's in water. Next one, big shot, again, Rowell. Okay, the Rowell group in UK comes up in 2003, same year. 2003 is very important for organocatalysis, and they come up similar way. The moment the Alder reports comes up of Diels-Alder reaction, immediately this group picks up and comes up with a fantastic name, Tadol. So this is what is Tadol. The aromatics or the aryl groups are naphthyls, okay? They name it as Tadol catalyst. They have given this name. So we gave our name, yeah? We can give this Arindam catalyst, for example, okay? So, you know, Dhutiman catalyst. We can give Dr. Harsha catalyst, yeah, many things, catalysts. So they gave Tadol catalyst, okay? So, you know, Tadol was, it's a big name. There is a name of a student also there. Yeah? You can read the name, okay? But they came up this paper in Nature. So you see the growth. We started organocatalysts in 1977 with publication in 1978, and in 2023 something comes up in Nature. By this time, organocatalyst has become so important that Nature thinks it very, very important to be published in Nature. Okay, so we develop the science like this. Yesterday I showed you how organosynthesis evolved slowly. This is how organocatalysis is evolved slowly. We started with LIGO 1978, publishing chota mota reports, and then something from the Rowell group comes up with Tadol, and they say that if you do this reaction in 20 mole%, we go for a hetero Diels-Alder reaction. No heat is required for this sort of Diels-Alder reaction, and in every case we get 70% yield, 99% enhancer selectivity, 97% enhancer selectivity, fantastic reaction. The HDA reactions are accelerated in protic solvents, as enantiomers preferred preferentially. But where is the chemistry? The chemistry is that at the end of 2003, we do a Diels-Alder reaction without heating it, and also in water, okay, and also in catalysts. So see the difference. Even today, if I ask my student that go and do a Diels-Alder 4+2 cycloaddition in Diels-Alder reaction, he will immediately go collect the starting materials. Sir, क्या करना है? Heat में बिठाना है. It comes to your mind, right, that I need to go to the fume hood, I need to put the temperature of 180 degrees centigrade and put the RB inside it. But it's not so. We need to be updated. We are in a position where you can use a 20 mole % of this catalyst to do a hetero-Diels-Alder reaction as reported by Rowell and also other groups. The next report in 2005, after 2 years, they come up with an axially chiral biaryl diol catalyzed hetero-Diels-Alder reaction. This is the molecule. Gets published in JACS, and they show that it's 20 mole %. They join 4+2, delivering a wide range of cycloaddition products, -40 or -80, depending on what starting material they have taken. And you can see 98% enhancer selectivity, 97, 99, 96%, 86%. See, there was a place where we had to think about 30% of enhancer selectivity. But you see, slowly it has tadol, then comes bamol. Okay, so these are all names given in dedicated to the scientists who worked in his lab. So gave these names, okay. But the chemistry is that we are in a position where an organocatalyst can deliver you a Diels-Alder reaction in lower temperature. No heat is required with fantastic enhancer selectivity, and that can be achieved with organocatalysis. Now, so what is solid phase synthesis? Solid phase synthesis is one of the techniques that we use widely, use polymeric resins in industries so that we can use it as a backbone and we can do different transformations, isn't it? Why it is required? Because that is heterogeneous. You can purify it, reuse it, purify it, reuse it. So we started thinking, or as the scientific community started thinking, that can we do something like towards this type of catalysts where you can go on increasing the chain length and come up with solution phase asymmetric strecker of aldehydes, and it was done. You can see that they have used these catalysts, slowly increasing the lengths. Why, I will tell you in the next slide. So 2 mole % of catalyst delivering fantastic enhancer selectivities, okay. Similar way we go on, other types of strecker reactions with resin bound catalyst. You need to understand these are all resin bounded. That means you have a solid phase and you have organocatalyst placed on that, so that we can remove it by filtration and go on one by one cycle. Why heterogeneous catalysts are better? Why it is better? We talk about homogeneous catalysis. So palladium catalyst is homogeneous catalyst, right? Okay, but is it better than a heterogeneous catalyst? No. Why? Because we cannot reuse palladium catalyst. Can we use Wilkinson catalyst? What is Wilkinson catalyst? Okay. Can we use palladium charcoal one more time? Hydrogenation. Billions of rupees per day, every day, we spend on hydrogenation reactions by palladium across the globe. Unquantifiable amount. You go to any industry in Pithampur, I can bet you that every day they spend at least 1 crore of rupees in hydrogenation reaction using palladium. We have approximately chota mota bada sab pakad ke 300 industries in Pithampur. If you visit, you can see 1 crore in here only, I will tell you. So if you calculate the homogeneous amounts catalyst, my group, we are very much, we are afraid of buying Gross catalyst. Why? 10 milligrams, 25,000 rupees. 10 milligrams, 10 grams of palladium carbon, 17,000 rupees plus GST. GST भी ज़्यादा है हमारे देश में, 18% है. कहाँ है? So you try to understand. At the end of the day, you can ask my students, they just come to me with 2.5 lakhs bill of chemicals, because that is the diet purchase, there's a limit. We go on 2.5, and if you find that at the end of the year, there's a huge list of catalysts, homogeneous catalysts, very expensive. That's why we also think that if we can combine organocatalysis with resin-based, because the only idea is that you can filter it, you can reuse it at least 2 cycles, 3 cycles, 4 cycles, that gives us, economic stability. And at the same time, when you do such reactions and we think that there's no loss of catalytic activity or productive enhancer selectivity was observed after 10 catalyst cycles. No loss of catalytic reactivity, no loss of enhancer selectivity after 10 cycles. This is something which is really, really amazing, and this get published in Anglo-Vande by the Eric Jacobson group. Very nice reaction. Okay, there are also similar examples which came up with the Strecker synthesis in ketoamines by the Jacobson group. One by one, they have used similar catalysts. I would send you the slides. You can go through this, that how they have gone through different backbones to keep up with the yield and enhancer selectivity, very high. Okay. Manic reactions. Okay, this is another part where we generate a beautiful CC bond reactions. Is it more electrophilic N-bocamine was found to undergo reaction. So it's not only the Michael reactions, not only the disorder reaction, but also in manic reactions, the Jacobson group had made immense contribution on using this type of catalyst. So please try to understand. We are talking about chemists like Jacobson, we're talking about chemists like LIGO, we're talking about chemists like Keiji Muroko. So it's not only the organocatalysis what we see in some time from the reports of List or Macmillan, but it's also the immense contributions in organocatalysis by other groups which we need to study to understand. Okay. Chiral phosphoric acid catalyzed manic reaction, and we all know that phosphoric acids have been very important, particularly inducing enhancer selectivities, and this is one example by the Fuchibei group where they show that they add this TMS ethers including this manic reactions with phosphorus based catalysts, so that you can beautiful the CC carbon additions with fine enhancer selectivities. All this coming up one by one. So it's again 2004 when we start working on these catalysts. I think we are in the last portions of the catalysis, or particularly the organocatalysis, and this is a report again by the Eric Jacobson group where we say a privileged, he writes in his paper as privileged dipeptide thiourea catalyst, and they use it in converting or addition of this phosphorus to the amines using this type of catalyst, and they say there's this alpha aminophosphoronate derivatives have very high antibacterial and antifungal activity. Okay, so this is the last slide what I show you on the on the attempts of organocatalysis. So my conclusions are up to this is that we started organocatalysis with feeble reports where we started using simple natural products like synconine, synconidine, and we are also using it now. Then try to functionalize it, try to add allyl groups, naphthalene groups or anthracene groups in the system, making it more stereoselectively very big. And we started publishing or started reporting, and we found that the enhancer selectivities were 30%, not more than that. We have been using a lot more organic catalysts earlier. We started with very high percentages. We used synconines, we used something like Tadol, we used something like solid based synthesis, and we also saw something like reports by Keiji Muroko where he uses a fantastic nitrogen backbones to create fantastic enhancer selectivities of 97%. So see the development. We started in 1978 with a group who reports in tetranet letters of 30% enhancer selectivity, and today we talk about 99% enhancer selectivity with 0.05 mole percent catalyst. Not only that, our concepts on pericyclic reactions like Diels-Alder reactions, we thought in some time that it cannot be done without energy sources like heat or even light, but organocatalysis shows out a way where we can understand that, okay, our Diels-Alder reaction, our hetero-Diels-Alder reaction, all can happen with properly designed organocatalysts. The third point is also, which is also very important, that prediction of reaction mechanisms. We are not talking about traditional classical chemistry of intermediates like carbocations, carbanions, nitrines, carbenes, etc. So the mechanism and the understanding and the yield is a bit changeable. We cannot explain in some cases that why the yield has decreased or why the change of the substitution has given a better enhanced selectivity. So there are concerns where we need to add more visions to organocatalysis. We need more instruments, I will say, more research infrastructure, I would say, to understand or look into the solution phase. If I tell you, can you use your specs or microscope to see that how this reaction is happening in your reaction flux? Can you say me? No, it's not possible. Or if I tell you that you put your hand inside and stop the reaction, can you stop the reaction? It's not possible, right? Can you do? Can you stop put your finger and stop one molecule to reacting with another molecule? Not possible. So I think when it comes to organocatalysis and we are using catalysts of such a big area, big molecule, there are many sites it's reacting. So we need better research infrastructure to exactly understand that what happens inside the reaction. It's not the classical carbocation or carbanion or SN1 and SN2 reaction that we can exactly tell that why it's happening 50% enhancer selectivity in one case and 97% in another case. But the conclusion is organocatalysis is a catalytic transformation. It's done by an organic molecule, so environmentally much friendly, much useful. At the same time, a mole percent of 0.5% of the catalyst can do fantastic transformation. Even we have proved that a pericyclic reaction can happen without light, without heat, in presence of an organocatalyst. Okay, with that, thank you for this. Okay, we stop the class here. Okay, it's okay, thank you. So, I think we can close it. Yeah. So, it's time for, so there is, okay, so there is a break, tea inside, okay. So we can, I think, go for tea. Then I think you all should be prepared for the examination, okay. And I think we should also do the grading in between. So we have some plans now when you have to do this grading. So you can go with the tea. Question papers kahan pe hai?